Here's an example problem. Refrigerant R134A enters an adiabatic compressor as a saturated vapor at 120 kilopascals at a rate of 0.3 meters cubed per minute and exits at 1 megapascal. If the isentropic efficiency of the compressor is 80%, determine A, the temperature of the refrigerant at the exit of the compressor, B, the power input, and show this process on a TS diagram. So fortunately, the problem statement gives us the schematic. We have here pressure coming out at 1 megapascal, pressure going in as 120 kilopascal. For this particular problem, we can draw a few assumptions. One, that this is definitely a steady flow problem, right? And two, you usually don't have to write this as an assumption, but I just wanted to iterate that the R134A is not an ideal gas, right? So you can't use the ideal gas law here. So you have to use E's or your property tables. So let's go ahead. First off, it's trying to find what is the temperature. We'll call this 0.2. We'll call this 0.1. What's the temperature of the refrigerant coming out? Not the temperature coming out if the process were isentropic, but the actual temperature coming out. Let's go ahead and see how we can do this. So for a compressor, the isentropic efficiency of a compressor would be the isentropic work over the actual work, right? So if you think about it, a compressor is a work-consuming device. The more inefficient the compressor is, the more work you have to put in to get the same pressure difference. So the isentropic work would be considered the minimum work. So that ratio of the isentropic work of the actual work, which is the definition of an efficiency for a compressor, was given as 0.8. So again, the isentropic work, this is in terms of specific work, right? Specific work per mass. So the isentropic work would be the enthalpy coming out of the compressor if it were isentropic minus the enthalpy going in, divided by the actual work, which would be the enthalpy coming out, actual enthalpy coming out of the compressor minus H1. Now, if I can get H2 actual, right, I can go to that can be one of two properties that I need to go to E's and to get my temperature. So let's go ahead and let's get these other enthalpies, because if I can get the enthalpy going in and the isentropic enthalpy coming out, I can solve using this efficiency equation for the actual enthalpy. So let's see how that works. Going in, I'm given that the pressure is 120 kilopascals and the quality is 1. With that, I take those two properties and I can find the enthalpy, 237 kilojoules per kilogram. Now, what I want to do is I want to find the isentropic enthalpy coming out, right? So I'm going to have to get the entropy at state 1, which in this case would be 0.948 kilojoules per kilogram Kelvin. State 2, right? The pressure coming out of the compressor, I always want it to be 1 megapascal, regardless of the efficiency. So what I would do is I would set the entropy at state 2 equal the entropy at state 1, and to use that value to get the enthalpy coming out of the compressor if it were isentropic. So that would be 281 kilojoules per kilogram. Now I'm going to get the temperature too, just to compare the isentropic temperature with the actual temperature. All right, now that I have that, I can use this equation, right? I'm going to go ahead and plug in my isentropic enthalpy minus the actual enthalpy divided by the actual enthalpy, which I don't know, minus the enthalpy going in. That equals 0.8. I do my math. I solve for the actual enthalpy coming out, which happens to be 292.3 kilojoules per kilogram. Now, for state 2 actual, again, the pressure coming out is 1 megapascal. Now that I have my second property, H2 actual, of 292.3 kilojoules per kilogram, I can solve using those two properties going back to E's to find out what the actual temperature is. And the actual temperature is 59 degrees Celsius. So it's interesting, if you take that temperature, the actual temperature coming out is 59 degrees Celsius, but the isentropic temperature, right, that's the temperature, if it was more efficient, the coming out would be less. So what's happening is the reason why the actual temperature is greater than the isentropic temperature is that all those irreversibilities that are inside the compressor, requiring you to put more work into it to get the same pressure difference, results in the fact that the temperature coming out is higher. Again, I'll say that again. The isentropic temperature coming out would be the temperature of the refrigerant coming out of the compressor when the compressor is operating at its most efficient, in its most efficient way. Right, so I'm compressing refrigerant from 120 kilopascals to 1 megapascals in the most efficient way. The temperature coming out is 48.6%. But but the actual work going in is much higher than the isentropic work to get the same pressure. So for the actual process, I'm still increasing the pressure from 120 to 1 megapascal, from 120 kilopascal to 1 megapascal. But because of putting in more work to overcome the inefficiencies, the temperature coming out is higher. Now, part B is asking you to find the actual the work done, the work in for this process. So if you were to do that, right, we're given in the problem statement. If you come back here, the problem statement, we're given that, here we go, the volume flow rate is 0.3 meters cubed per minute, right? So that's at the inlet. The volume flow rate at the inlet is 0.3 meters cubed per minute. So with that, we should probably go back, and at state 1, you can get the specific volume, right? So that specific volume would be 0.16212 meters cubed per kilogram. We use that to find the mass flow rate. So if we're trying to do part B, we can get the mass flow rate. It's going to be the volume flow rate going in divided by the specific volume. We can get that the mass flow rate of refrigerant is 0.0308 kilograms per second. And if you were to do a first law analysis on an adiabatic compressor, you can get that the work in is going to be mass flow rate times the enthalpy out minus the enthalpy in. We're going to use the actual enthalpy since we're trying to find the actual work in. So if you plug in your numbers, you get 1.7 kilowatts worth of power to the compressor. Now, the last part of the problem is asking you to draw what's called a TS diagram. So let's look at how we would do that. So we have temperature on the y-axis and entropy on the x-axis. And since this is refrigerant, right, it's mainly used during phase change processes, we have our saturation curve. So we have the low constant temperature line for a pressure of 200 kilopascals. And then we have the upper pressure line, which is a pressure of 1 megapascal. Now it tells us that the state of the refrigerant going into the compressor, right, state 1, or the state going into the compressor, is saturated vapor at 200 kilopascals. I believe no, I'm sorry, not 200 kilopascals. It'd be 120 kilopascals. And it is being compressed to the upper pressure line, but with some entropy production that would be state 2 actual coming out of the compressor at 1 megapascal. Now, the isotropic process, right, and it's not asking us to draw the isotropic process, but the isotropic process would be represented by a straight line from state 1 to state 2 isentropic. So you can see that the actual compressor process results in some entropy production.